So this talk is based on some work which I did with my master's student around 2 years back, and it was published this year in January in the Journal of Statistical Mechanics. So to briefly introduce myself, I'm Dr. Colin Benjamin. I'm Associate Professor in the National Institute of Science, Education and Research here in Bhubaneswar in India. And it comes under the Homi Bhabha National Institute. You can learn more about me in my homepage here. And also I'm on Twitter, Facebook and LinkedIn. So let's start with the abstract. So the main purpose of the work was to devise a better PageRank algorithm than what Google search offers. So Google search works on a classical computers, on classical environment. But if we had a quantum internet kind of framework, we had quantum computers, or at least the NISQ variety of quantum computers, and we have connections between them, can we devise some algorithm which works better than the PageRank or the Google's famous PageRank algorithm? And the aim of this paper was to show that yes, we can, through what are called quantum stochastic walks, and we use two independent models to model quantum stochastic walk. That is the only incoherence model and the dephasing with incoherence. And we show that degeneracies, that is web pages which have the same rank and therefore lead to a worse search outcome, can be resolved by quantum stochastic walks, or what we call the quantum PageRank algorithm. We look at small world networks, which are a proxy for the internet, and in those, especially many of those networks, we find that the quantum PageRank algorithm is much better in resolving degeneracies as well as converging to the ranks in minimum amount of time than the classical PageRank algorithm. So this work was published in Journal of Statistical Mechanics, and you can download it here. So basically, what is the Google PageRank algorithm? So two basic parameters or two efficiency parameters are behind the PageRank algorithm. First, the degeneracy in ranks, and second, the convergence time. So any algorithm has to return the least degeneracies among web pages, and then it has to converge fast to those ranks. So if we go back 20 years before, when I was a PhD student, we had pre-Google search engines like Lycos, LookSmart and all, and the user gave a search query, and a whole host of websites with some matching content was listed in no particular order. But what Google did was it added a second step to this. It ranked those websites with the matching content based on the links these different websites had between them. To do this second step, it relied on what is called a continuous time random walk. I will describe that in a brief time. And so basically what it did was the website with the highest rank was listed on this network of websites, which has a very high number of links to itself. So it's a highly connected node or a vertex in a network. And this node or vertex will possess links from other very highly ranked websites, and therefore it gets a high rank by itself. And you can learn more about it in this paper and also in Wikipedia and this book by I. Rogers. So what is behind the classical PageRank algorithm? This is called the classical continuous time random walk. So any network, any complex network can be modeled as a graph with m vertices and e edges. And to model a network of different websites, the vertices would represent the web pages and the edges would represent the links from one web page to another. To understand a graph, we have to build what is called an adjacency matrix, and it has entries Aij is 1 and J to I means jth vertex to ith vertex is 0 if the edge is directed from vertex J to vertex I. And if it is undirected, then both the weights Aij and Aji are 1. The out degree of a vertex is defined as the total number of edges leaving the vertex, and that's defined as the sum of these weights. And to hop between one web page to the other, we have defined what is called gamma, the transition rate. So to start with, we define what is called the generator matrix, which is built from the adjacency graph, adjacency matrix of the graph, and it has, if on the same vertex, it carries the weight dj, which is the out degree of the vertex, multiplied with gamma, the transition rate, and for different vertices, it has the weight minus gamma. So in the language of web pages, adjacent vertices of websites are those between whom an edge or a link exists. One can build what is called the transition matrix, which is defined as the probability of transitioning from vertex j to vertex I during a short time interval epsilon. You can do a brief calculation that has been done in this book on quantum walks and search algorithms by Renato Portugal, and you can understand how this process evolves. I'm not going into detail, but you can find it in detail. So finally, we end up with a probability vector at some particular instance of time. What is this probability vector? It has the weights or the ranks of all the web pages which you are searching over at a certain instant of time, and it is built by the time evolution of your translation matrix multiplied with your initial probability vector. So you start your search from certain vertex site, and you end up at a certain, after a certain amount of time, at another series at another vertex, and you define this as the probability vector. Now, if you iterate this equation over and over again, we eventually reach what is called the stationary state. And in the stationary state, the ranks of the different vertices, they are the entries of the stationary solution, and they correspond to the various weights of your web pages. And the highest ranked web page here would be the one with the highest weight in this probability vector. But we work on what is called the Google matrix, and in the Google matrix is defined with the adjacency graph as I was defined in the last slide, but we add a factor 1 by m, where m is the total number of vertices in your graph, and this is to avoid dead ends, because in directed graphs, if you continuously click from one link to another, from one web page to another, you may go to a site which has no further links, and in that is called a dead end, and you want and your search will end there. We don't want that to happen, so you add a factor of 1 by m there, so that if you reach a dead end, there is a finite probability of getting out of it as well. Now the factor alpha, which we choose here, which is the weight of this ratio of the random jumps from the original graph edges of the graph, can be minimal, and we therefore choose alpha. Generally it's chosen to be large, around 0.9 or 0.85, and that works for any directed graph. Now if your graph is undirected, as a quantum graph would be, because it's a unitary matrix and evolution is unitary, and we are working on Hamiltonian, which is Hermitian, a quantum Hamiltonian, which is Hermitian. Therefore, we have to go to undirected graph, and therefore we have to have a very realistic comparison between the classical PageRank and what the quantum PageRank offers, because quantum PageRank can only work on undirected graphs. Therefore, we find the classical PageRank for both directed as well as undirected graphs. So we start with a very basic example here. This is a 8-vertex graph. It's a directed graph. We first build the adjacency matrix, give a finite value of alpha. This highlight centrality is a piece of code which you can find in Google. And then using the page rank centrality, it's an inbuilt Mathematica function. You can calculate, give finite value of alpha, the classical page rank for this vertex. And then you can count the distinct number of vertices, which will be a efficiency benchmark for how many vertices can be perfectly resolvable. And for this 8-vertex graph, which is drawn here, this is the adjacency matrix, we find that there are 2 of these vertices which share the same rank. For example, here vertex 1 and 4, here colored yellow, share exactly the same rank, so they are basically unresolvable. Along with that, vertex 6 and 8 are also bearing the same rank. Again, they are unresolvable here. So there are a number of distinct ranks in this 8-vertex graph are 6. Therefore, the degeneracies, there are 2, and they are unresolvable. So classical PageRank does okay, but not very good as far as directed graphs are concerned. Now, if we convert this undirected graph to a directed graph, this short piece of code, and again run the same PageRank centrality algorithm, and because it's undirected, now there are no dead ends, so your alpha value is 1, and do a distinct count of the number of vertex ranks, what do we find? We find worse. Classical PageRank actually performs much worse than what it did for a directed graph. For an undirected graph, we find vertices 1, 4, and 5, as well as 7 bear the same rank, 0.1 to 5, while vertices 2, 3 have the same rank, along with vertices 6 and 8. So basically, there are just 3 distinct ranked vertices. The rest are all degenerate. And because they are degenerate, they are very difficult to distinguish, and therefore classical PageRank performs very poorly on undirected graphs. Now we can do the same thing for a small world network, which is a proxy for a internet. This is a Watt-Strogatz graph distribution with 100 vertices, and this is the value which determines how close the Watt-Strogatz distribution is to a real world network. So generally one takes values between 0.01, 0.02 to determine this. So in this case also we run the classical PageRank algorithm here using this PageRank centrality command, and we find that it has distinguished well for our directed Watt-Strogatz network. It has 94 of these vertices have distinct ranks, and therefore there are only 6 degenerate vertices here. Now if we convert that Watt-Strogatz network to an undirected graph and run again the PageRank centrality or the classical PageRank algorithm, we find it again performs very poorly. The number of distinct vertex ranks are now only 13. So from 94 it has come down to 13. So 87 of these vertices share the same weight, and therefore they are unresolvable. So as we saw, the classical PageRank performs very poorly on undirected graphs, while it performs much better for directed graphs. Now let's understand what is the quantum stochastic walk, which is the bedrock of the quantum PageRank algorithm. Now, quantum stochastic walk are used to model quantum processes that are coupled to the environment. We replace our probability vector, which we had for the classical PageRank algorithm, which are density matrix, which represents for the quantum case the quantum walker at time with dimension dependent on the number of web pages or number of vertices in your graph. So M here is the total number of vertices, and we denote as the basis states this kex, and any density matrix element in this matrix can be found by this inner product of the ith and the jth vertex. To evolve this in classical PageRank algorithm, we had the translation operator, which will determine the probability vector at some other instance of time. Here we use what are called the Kozarski-Lindblad master equation, and they determine how your density matrix will evolve in time. I'm not going deep into it, but if you want to read, you can read these 3 papers which deal with it much more elaborately. There is a parameter omega here which determines the quantum to classical transition. So this part here, minus I to 1 minus omega h, the commutator of h and density matrix, is the continuous time quantum walk, purely quantum part, and this second part is the purely classical part determined by omega here. If omega is 1, then your density matrix evolution reduces to the classical continuous time random walk. Ox represents the Lindblad operator, and depending upon what kind of this operator you choose, we will have 2 distinct kinds of walks. One is the only coherence, where only the off-diagonal elements of this operator are affected. So these are only correspond to the off-diagonal elements, and they are weighted via the generate a matrix from the adjacency graph of your Google matrix, and dephasing with incoherence, which affects all the elements of your adjacency graph. To solve it, we start at some vertex, which is basically a web page, at some instance at, say, time 0, and then we evolve it using this operator O, and after a finite amount of time, we find where we are, which is rho bar T, which gives us the probability of occupation of those websites. So we use the quantum stochastic walk with either only incoherence or dephasing with incoherence to rank all the vertices of the network. And there is another method in quantum stochastic walk called pure dephasing, but in its stationary state, it returns the same rank, so we don't use it here. And for all the calculations related to PageRank, we use different values of our omega. Omega, as I said, is a parameter which interpolates between pure quantum walk and a pure classical walk. And we find the omega for which it takes the shortest amount of convergence time. And the shorter the time, the better the PageRank algorithm. So by convergence time, we mean the time it takes to the classical PageRank algorithm or the quantum PageRank algorithm to converge to the equilibrium state, PEQ in case of classical PageRank, or rho EQ, where rho is the density matrix in terms of quantum PageRank. Now there are two benchmarks, as I said, which distinguish the efficiency of your algorithm. One is the number of degeneracies, and the second is convergence time. So to calculate the number of degeneracies, as I said earlier, we find the probability vector in case of classical PageRank, and we find the density matrix in terms of quantum PageRank at a finite amount of time, and that means in the stationary state, what are the weights of these different vertices we have, and that defines the PageRank, and that defines whether we have degeneracies or not. And the convergence time, the time it takes from your initial state to your stationary state, how long it takes, and that's defined by this Frobenius norm of your density matrix elements. If the square of the Frobenius norm is less than some tolerance level, we put this epsilon to be very small, and if these, after you have a finite iteration to your stationary state, if the difference between t plus 1 and t is much less than epsilon, then we say that we have reached that stationary state, and the time it takes to reach that stationary state is your convergence time. So if the convergence time of quantum PageRank is better than classical PageRank, then we expect that tau QPR is less than tau CPR. And for our internet networks, we choose small world networks, and they can come in various types. One is the scale-free network, which follows a distribution law given by this. Pt goes as d to the power minus h, where d is the vertex degree. And the examples are like Barabasi-Albert price graph. These are all inbuilt Mathematica functions. You can just generate them by giving the right command. Then we have the Watt-Stochash, which we will work on. Then there is Erdős-Rényi spatial networks. So all these networks possesses three essential properties. Any two nodes has a very relatively small distance between them. There is a lot of clustering between them, and there are hubs are present. So what do I mean by clustering? So let's assume that I have a node or a vertex A which is connected to two other nodes B and C. Then there are chances that B and C themselves are joined by an edge. That means all A, B, and C are mutually connected, and that's called a cluster. So in these type of networks, there are lots of clusters. And hubs are vertices which possesses a large degree. So let's first look at our code to calculate the convergence time. So to use this, you have to download what is called the quantum stochastic walk package. It's a Mathematica package for quantum stochastic walks on arbitrary graphs, which was developed by Peter Fallon, Jeremy Rodriguez, and Jingbo Wang in this paper. It's free to download. And we first apply it to the vertex graph. First, save this in your Mathematica notebook, and then you call this QS walk package, and then you start your code for this is for the convergence time. Again, we have our 8 vertex graph This is a directed network. This is the matrix plot of that. And as I said, you find the convergence time given a certain value of epsilon, which is very small. So you expect that this t is 400 here. That means it would go to the stationary state much before you reach 400. You give a value of omega, it's 0.1. You start your omega at 0.1 and you increment it in steps of 0.1. And you run your quantum stochastic walk. You call your adjacency matrix H. You have already designed your Lindblad operators here. These are how you design your Lindblad operators. The gamma, which I said was the transition matrix element. Give a value for gamma. Here we have given gamma 1. That's a reasonable estimate to give. And then you multiply with your Google matrix, and that's your Lindblad operator for all the for the dephasing and incoherence model. And for the only decoherence model, you remove the diagonal part through this. So this list here tells you how to do it. I'm not going into detail. So this list 2 is only the diagonal part of your matrix, and you can remove it. And you start your vertex at some index. So here we start that all our vertex sites are equally probable. So it's 1 by n. So all the diagonal sites are your vertex sites, and they're equally probable to be occupied at equals to 0. And you start your evolution at that time. So from row 0, and you evolve it till TF using your Lindblad operators, and H is your adjacency matrix. So we first do it for this quantum stochastic walk, and for the classical PageRank, we use the inbuilt PageRank centrality of Mathematica. So the tolerances, I said, we give us very small number, 10 to the power minus 6. So we run this code. This code is freely available here. And at the end, we look at our plots. So this is for the 8 vertex graph, and you can see for finite values of omega between 0.4 and 0.6 and around 0.5, it actually is much better than the classical PageRank. The convergence time is less than 1. So for classic, we have normalized it with respect to the classical PageRank. So the classical PageRank is almost like 30% more time it takes for this 8 vertex graph. And similarly for this, both the models, the quantum PageRank with dephasing and incoherence as well as only incoherence. Okay. So this was for the 8 vertex. Now we take a general 100 vertex graph, which is a real world network, an internet. And here too we see, so this is the graph here. And here also we see the quantum PageRank is much, much better in this case, especially for the Watt-Stroke axis. And you can see for all range of values of omega, starting with 0.1 to almost like only when omega goes to the classical PageRank limit do we find that it attains classical PageRank. Otherwise, all values in the quantum PageRank limit, we find the quantum PageRank much, much faster, almost like 1/5 of the time it takes for the quantum PageRank to converge to the stationary state. So now we finally calculate the vertex ranks. This is the 8 vertex graph. Again, we run the code as given here. I'm not going into detail. And then we find out the number of distinct vertex ranks via both quantum PageRank with dephasing and incoherence, quantum PageRank with only incoherence, and then for both the classical PageRank, the undirected graph as well as the directed graph. So this was our 8 vertex graph. And we have already seen in the 8 vertex graph, we have the first and the fourth site degenerate along with the 6th and the 8th site, and the same thing we see here. So the distinct count is 6. So there are only out of the 8 only 6 vertices which have a distinct count. And when we go to undirected, from this is the directed one which has a distinct count of 6. When we go to the undirected one, now we see it. The classical PageRank performs much poorly, and we have only 3 here. So there are only 3 vertices which have distinct ranks. The rest of the are all degenerate. But for quantum PageRank here, of course, quantum PageRank runs only on undirected graphs. We see this both for this quantum PageRank with dephasing and incoherence and quantum PageRank with only incoherence. We have 7 distinct vertices. You can see all of them are distinct. Only vertex 1 and 4 has the same rank, while the rest of the vertices are all different and distinguishable ranks. So with quantum PageRank with dephasing and incoherence, we have 7 distinct ranks. Only incoherence, again 7 distinct ranks. That means all out of the 8, 7 can be distinguished perfectly. But for the classical PageRank, only 3 can be distinguished perfectly in the undirected case, while for the directed one, 6. So this is a plot versus vertices, the PageRank weights, and you can see it here. And then finally, we run it on the Watt-Strogatz, which is a 100 vertex graph, which is a proxy for the internet network for this value of P 0.025. And herein also we see the quantum PageRank with dephasing and incoherence can distinguish all the vertices perfectly well, 100 out of 100. While for the classical PageRank, the undirected one really performs poorly. Only 3 of those can be distinguished. The rest are all degenerate. While the classical PageRank, the directed one, 93 of those ranks can be distinguished perfectly. So with this, I would like to end. Thank you so much for your attention. So there's just one question. So benefits of using Wolfram language for my presentation. Well, with Wolfram only, it gives the number of networks. So I only showed the graphs related to Watt-Strogatz and the 8 vertex graph. So some of this can also be done in Python, but not as beautifully as can be done in Mathematica, because you can just call these networks ADOS, Renyi, Spatial, this 100 vertex graphs, the scale-free networks, and they are all inbuilt in Mathematica. The classical PageRank, as I said, is an inbuilt function in Mathematica. So that makes it much more easier to deal with than if I had to work on Python or any other software.